Welcome back, AP Statistics. This is Chapter 13, From Randomness to Probability. This is the first of several sections that will be focused primarily on probability. So let's talk about random phenomena first, like flipping a coin or rolling a die. A random phenomenon is a situation in which we know which outcomes can possibly occur, but we don't know which particular outcome will happen. Each occasion upon which we observe a random phenomenon is called a trial. As each trial transpires, we note the value of the random phenomenon, which we will call the outcome. So we run a trial, and that trial produces an outcome. An event is a set of one or more outcomes. So an event can be fulfilled sometimes when a particular outcome transpires, and an event can sometimes be fulfilled when one of several outcomes transpire. And those are different kinds of events. We'll talk about that. A simple event is an event satisfied by only one outcome, whereas a compound event is an event satisfied by more than one outcome. Pretty simple, not too compound. The set of all possible outcomes of a random phenomenon is called the sample space, which we normally denote by the letter S. Makes sense. So for example, the sample space of a coin flip is, well, sample space equals, and then we see these little squiggly brackets right here. That's proper notation. You have heads, comma, tails. We have two elements. The sample space for a six-sided die roll is S equals, and then we have our squiggly brackets and each of the outcomes associated with a roll of a fair six-sided die. Here's a diagram of a random phenomenon. We have several possible events. So we have a compound event, and a simple event. A compound event can be satisfied by multiple outcomes, so can this one, of course, but this simple event can only be satisfied by one outcome. Collectively, the set of all the outcomes, not seven is the number of outcomes, that's the size of the sample space. The outcomes themselves comprise the sample space. So the sample space is the set of outcomes themselves in squiggly brackets separated by commas. The number of outcomes is called the size of the sample space. There are 7 outcomes, but for the sample space, we would list out each of these outcomes in those squiggly brackets, right? Now that's a commonly confused thing, the sample space and the size of the sample space. So let's find some sample spaces here. We're going to find the list of elements. So find the sample space of the following random phenomena. Then we're going to state whether or not the outcomes are equally likely. So rolling a die and then flipping a coin. This one I'm going to do right here for you because it involves 2 parts. We roll a die and then we flip a coin. So each one of our outcomes is going to have multiple components to it, if you will. Check this out. The sample space is equal to, okay, here's our first outcome. We roll a 1 and the coin lands on heads. We could also have 2 and the coin lands on heads, 3 and the coin lands on heads, 4 and the coin lands on heads, so on and so forth. And then we get to a 1 and we get tails, 2 tails, 3 tails, so on and so forth, all the way to a 6 with tails. All right? So there are 12 total outcomes, 6 rolls of a die, 2 flips of a coin. 6 times 2 is 12. And that would be the sample space there. You'll notice how I use some parentheses within my squiggly brackets, and that's because each of the outcomes has 2 parts, the die roll and the coin flip. Now we're going to talk about rolling 2 dice and recording the lowest number. Think about this one. I wouldn't say it's a trick question, but it'll make you think a little bit. What would the sample space be if we're only recording the lowest number? Pause the video, try this one on your own, and see if you're right. Okay, I'll assume we're ready to continue. Here we go. The sample space would be, well, the same as a normal roll of a six-sided die. What gives? Well, if we're recording the lowest number, and our lowest number is a 1, that's conceivable. It could be a 2, a 3, a 4, a 5, or wait, a 6? Yeah, we could roll 2 6s. In that case, 6 would be the lowest number because it's the only number we would roll. So this is actually the same sample space as the roll of a six-sided die in general. Interesting. So a dog has a litter of 4 puppies, and we record the number of males, all right? We're not listing out all the possibilities of male and female dogs. We're listing out only the number of males. So try this one. See if you get it. Pause the video and check your answer against mine once you're done. Okay, I'll assume we're ready to continue. Here comes the sample space. The sample space is, well, we could have no males, all females. We could have 1 male, 2 males, 3 males, and all 4 males. Those are all possibilities. Now we need to talk about something called the law of large numbers, theoretical probability and observed probability. Probability that comes from a mathematical model and not merely from observation is called theoretical probability. So if we are observing a random phenomenon and we know how it's going to work mathematically and we have a model that we can use, that is an example of an application of theoretical probability. We use a model to make predictions based on math, and we don't just observe outcomes and find what proportion of those outcomes turn out one way versus another versus some other way. So this is opposed to observed probability, which I've just described, which is the proportion of times an event is noted to transpire out of n trials. So it's a proportion. How many times did it happen over how many trials did you run? I may observe that I get 7 tails out of 10 coin flips. This is entirely conceivable, not an absurd result. So my observed probability is 7 out of 10. Now, does that mean that the theoretical probability of getting tails is 7 out of 10? Well, not so. My theoretical probability for getting tails on a fair coin is 1 out of 2. Now, some of you who know a bit of physics will say, Mr. DeClerico, a quarter, a US quarter, favors heads. That is true, right? That is true. You're not wrong about that. Because of the weight distribution of the coin, it does favor heads very slightly, but you would need to run hundreds, if not thousands of trials to see that disparity in probability between heads and tails of a quarter show up. We're going to assume the coin is fair, which means it's just as likely to turn heads as tails. And no, smart Alex out there, we are not considering the case in which it lands on the rim. Okay, that is extremely unlikely even for a fatter coin like a nickel. For a random phenomenon with equally likely outcomes, our model for the probability of an event A is the number of outcomes in A, that's how many outcomes satisfy this event. Remember, events can be satisfied sometimes with only one outcome and sometimes with multiple outcomes. So the number of outcomes that satisfy the event A that we're concerned about over the number of possible outcomes in total. And the big question is, okay, it seems simple, it makes sense, but how do we know that is actually how probability works in the long run? So we need to talk about the law of large numbers, okay? The law of large numbers says that if we repeat a random process, the proportion of the number of times a particular event occurs approaches a specific number, namely the true probability of the event occurring, okay? So again, to our question, how do we know that a model is right? We know a model is right by running the law of large numbers. We observe many trials. And once we do that, if the probability the law of large numbers gives after many trials of an event occurring agrees with our model, we can vindicate our model, okay? Because the law of large numbers says as we increase trials, the observed probability will approach the theoretical probability. The probability that we observe after many trials will approach the true probability. And that's a way we can vindicate our model. All right, we can show that it is legit. So, a working definition of probability. For any event A, probability of A is equal to the number of times A occurs over the total number of trials in the long run. All right? In the long run. That is a definition of probability, and it implies that we can take a model and verify it with the law of large numbers. In other words, the observed probability of an event approaches the theoretical probability after a large number of trials. I've said it before. I'll put it in print so you know it's important. Let's make an accumulated percent graph of the number of heads we get for 10 coin flips. And we'll do that on the next slide. We'll observe that after many coin flips, the probability of heads is 50%, or probability of H for heads is equal to 0.5. So this is a neat little coin flip application that I found online. If you can get the references for both heads and tails, I will be impressed. But let's flip this coin. Here we go. All right, we flip the coin and we get tails. All right, let's flip it again. And we get heads. Flip it again. And we get heads again. Flip it again. And heads. And heads. 4 times in a row. Wow. And tails. Tails again. And heads. Whoa, is that a triple flip? All right, landed on heads. And it looks like we have one more to go. And heads. There we have it, 10 flips. Here is the accumulated percent graph. We have the trial number on the x-axis and the accumulated percent of heads. If you recall, the first coin flip ended in tails, so we're at 0%. Then the second coin flip landed on heads, so we're at 1 out of 2 heads, 50%. The one after that also landed on heads, so 2 out of 3, then 3 out of 4, and then 4 out of 5, and then we start getting a string of 2 tails in a row. So we have 4 out of 6, or 2/3, and then 4 out of 7, or about 0.57. And then we get a string of heads, 3 in a row, that put us a bit above this 50% mark. But something you should notice, at the very beginning, things are rather volatile. We were either at 0% heads or 100% heads, and then we get to that 50% mark, and then we have a bit of an arc going on, and then we work our way back. And this second arc is a little less pronounced, and that's because as we increase the number of trials, and 10 admittedly is a small number of trials, but I don't want to waste your time. If we increase the number of trials, this 50% mark right here with this yellow line kind of acts as a magnet, because if it is true that we're equally likely to land on heads or tails, the law of large numbers would say that as we increase our number of trials, that the accumulated percent, the percent of heads, would get closer and closer to that 50% mark. So yeah, there may be some arcs here and there, but they'll be less pronounced as trials continue. So the law of large numbers is pretty cool, but there are some assumptions that we make before we know that it's going to work out. So the law of large numbers holds given 2 key assumptions. First, the outcomes, and therefore the events, which may consist of 1 or more outcomes, must have the same probability for each trial. And events must be independent, meaning the occurrence of one does not affect the likelihood of any events after it. So the outcomes must have the same probability for each trial. We can't change up the rules of how the probability works from trial to trial. And similarly, the events need to be independent, which means the occurrence of one event does not affect the likelihood of any events after it. I've said in a previous video that the two most important words in statistics are significant and independent. And here we go, independent. Two events are independent means that the occurrence of one does not affect the likelihood of any of the events after it. So, to clarify, several coin flips are said to be independent. The occurrence of heads on one coin flip does not affect the probability of getting either heads or tails on the next coin flip. However, if you choose a jack from a deck of 52 playing cards, so no jokers, but 4 suits, 13 denominations, so we choose a jack from the deck of 52 playing cards, not replacing the card, and then choosing the queen, those would not constitute independent events. Since we did not put the jack back, that altered the probability of picking the queen. So those would not be independent events because we did not return the jack to the deck and then shuffle. So now let's talk about how we might misapply the law of large numbers. You've just flipped a fair coin. Well, actually not just any coin. We're flipping a Doge coin because why not? And we've seen 6 heads in a row. That is a possible result, but not terribly likely. Here's the question. Does this Doge coin owe you some tails because you got 6 heads in a row? Suppose you spend that coin and your friend gets it in change. When she starts flipping the coin, should she expect a run of tails to, even things out? You might think that the coin is going to even itself out pretty quickly because 6 heads in a row, that's rather unlikely, and the odds are 50-50, so shouldn't there be a little bit of a reset happening? Well, that's actually not true. Why shouldn't your friend expect to see a run of tails? Well, think back to that whole idea of independence. Coin flips are independent. So if I get 6 heads in a row, heck, if I got 10 heads in a row, I am no more or less likely to get a heads or a tails, even with a Dogecoin. So we're going to talk about this logical fallacy. It's called the law of average or the gambler's fallacy. The law of averages or the gambler's fallacy. All right, and what a way to follow up a Dogecoin, but with an actual meme. Recall that the probability of an event is the number that the law of large numbers settles on in the long run. So what is probability? Probability, the odds of an event happening, is the proportion of successes that the law of large numbers settles on in the long run. That's why we call it the law of large numbers. We need a large number of trials, not a small number of trials, to determine the true probability of an event. The law of large numbers does not say that an outcome is more likely to occur if it hasn't in a while. In other words, that the law applies to the short run as well as the long run. So going back to this example with the coin, yeah, sure, we got 6 heads in a row, but the coin is under no obligation to fix the odds back to 50% in the next couple of coin flips. So, for example, if a 6 hasn't been rolled on a fair 6-sided die in a while, someone who hasn't taken statistics might insist that they are due for a 6. They're due for a high roll since they haven't got one in a while. And that is a fallacy, of course, because just like coin flips, die rolls are independent. One die roll does not affect another. And that logical fallacy is called the law of averages or the gambler's fallacy. So believing that one is due for a particular outcome is a failure to acknowledge the independence of the events in question, right? If we are assuming independence of events, we cannot say, by the definition of independence, that one event is more likely to occur after a string of events happened before it. That is a logical fallacy.